In this module, we shall discuss the nested intervals theorem and the Archimedean property, which are more intuitive consequences of completeness. In the next module, we will in fact show that together they imply completeness, but individually they might not. So we first begin with a definition. This is the familiar definition of intervals. Okay. Let F be an ordered field, and A comma B be elements of F with A less than or equal to B. We define the following four sets denoted the following way: A comma B, this is X in F, such that A is less than X less than B, comma, closed, this is supposed to be, the first one is supposed to be the open interval, second one is the closed interval, is X in F such that A is less than or equal to X less than or equal to B. Then we also have these half open half closed type intervals. This is just X in F such that A is less than or equal to X less than B, and A comma B closed. This is supposed to be X in F such that A is less than X but less than or equal to B. Okay. So the first one is called the open interval, the second one is called the closed interval. Let me just make this remark that don't get confused with the ordered pair AB and the open interval AB. Both have exactly the same notation, and not a single instance in your mathematical life should you ever get confused which is which. So now that we have defined what these intervals are, we can state the nested intervals theorem. Before that, let me just talk about index set. So suppose G is a set. Okay. Now we want to refer to an indexed collection. That just means that I consider a function I, consider the function f from another set I to G that is bijective. Okay. So suppose G comma I are sets and consider a function f from I to G that is bijective. Then obviously I can consider the elements of this set G as some Gi where I is coming from capital I. What I am essentially meaning by this is this Gi is nothing but f of I. Okay. So essentially what I have done is I have parameterized the elements of G by this set I. This set I is called the indexing set. This is called the indexing set. So the elements of the set G, which are themselves sets, if you recall our module on axiomatic set theory, can be parameterized by the set I. Okay. So when G is parameterized or indexed by natural numbers, we often write Gi I coming from N. Okay. This is just a shortcut notation for there is a function f from I to capital G that is bijective. I am just representing the collection G in a different manner. Okay. Now this is just a notation, don't worry about it too much. Let me now state the nested intervals theorem. Nested intervals theorem. Okay. This states the following. Let F be a complete ordered field, and let II, which is equal to AI BI, indexed by the natural numbers, be a collection of closed intervals that are nested. What do I mean by nested? What I mean is for all j in n, ij plus 1 is a subset of ij. That's what I mean by nested. Then intersection I equals 1 to n, ii is non-empty. Okay. So what this says is I have a collection of intervals that are parameterized by the natural numbers, closed intervals, that is very crucial. Then it turns out that when I take the intersection of all these intervals, I get the empty set. I don't get the empty set, sorry. I completely reverse the conclusion. I don't get the empty set. Proof. Before I write down the proof, let me just sort of illustrate what this is saying. This is saying that if I have closed intervals that get smaller and smaller, then it cannot happen that the intersection of all these closed intervals is empty. Now, when will this intersection be empty? Well, if these intervals sort of cluster around a hole. So the nested intervals property is sort of saying that there are no holes in the real numbers. I will elaborate on this further after I give the proof of this theorem as well as the Archimedean property. Okay. Now, how do I prove this? Well, define S to be the collection of AI such that AI is in N. Note, II was just AI BI. So I have these closed intervals. I'm just looking at all the left hand points and putting them in a set. Note that because AI plus 1 comma BI plus 1 is always going to be a subset of AI comma BI for all I in N, it immediately follows that AI plus 1 will in fact dominate AI, which will in fact be less than or equal to BI plus 1, which will be less than or equal to BI. Okay. This shows that each BI is an upper bound for S. Okay. Now let U be by definition the supremum of S. Why does the supremum exist? Well, because we took a complete ordered field. Because we considered a complete ordered field, the supremum exists. So define U to be the supremum of S. Okay. Now, by the very definition of the supremum, in fact, property 2, we must have U is less than or equal to BI for all I in N. Why is this the case? Because each BI is an upper bound for S, the supremum will have to be lesser than any upper bound. Similarly, because U is an upper bound, this has to be greater than or equal to every single AI. In other words, U is an element of AI BI for all I. which is same as saying u is there in the intersection I in n, I. Okay. So we have found an element u that is there in the intersection. U is there in the intersection. Okay. So this concludes the proof of the nested intervals theorem. Now we come to the second intuitive property possessed by complete ordered fields called the Archimedean property. It is said that the great Greek mathematician Archimedes remarked that, "Give me a lever long enough and a place to stand on, and I shall move the earth." This is nicely illustrated in this engraving from Mathematics magazine, published all the way back in 1824. The next theorem, known as the Archimedean property, illustrates this phenomenon in a complete ordered field and is named in his honor. The Archimedean property. The Archimedean property. Archimedean property. Let F be a complete ordered field. Suppose x comma y in F are both positive. Then we can find a natural number n in n such that nx is greater than y. Okay. Note that the natural numbers and indeed the rational numbers are always sitting inside an ordered field. So here and henceforth we shall not make any explicit mention of this. Whenever I take a natural number and multiply it with an element of a field, it is to be understood that I am considering the natural number as sitting inside the ordered field. Okay. Same is true for rationals. How does one prove this? The proof is surprisingly quite easy from completeness. What you do is you consider the set nx such that n is coming from the natural numbers. Look at all the multiples of x by natural numbers. If our result is not true, then the set S is bounded above, right? In fact, y is an upper bound. Okay. By completeness, S must have a supremum. Say small s. Okay. Or rather, let's just, instead of confusing with too many s's, let's just say small u. Now you have u minus x is less than u. Why is this the case? Because x is greater than 0. But by the second property of supremum, and since u is the supremum, we can find s in s such that u minus x is less than s is less than or equal to u. Okay. But s comes from the set capital S, so I can write this as u minus x is less than n naught x is less than or equal to u for some n naught in n. Okay. Now just considering the first part of this, u minus x is less than n naught x. This implies that u is less than n naught x plus x, which is n naught plus 1x, which is an element of S. Okay. This contradicts the choice of u as the supremum. It has to be an upper bound in the first place. It's not. This shows that u cannot be the supremum. So our assumption that the set S was bounded above is wrong, and we are done. The Archimedean property is proved. Now let me give you an exercise showing Archimedean property, which I'll abbreviate as AP, for Q is very easy. You don't need to do any of this complicated stuff. Do it. Okay. Fine. So we have now shown the Archimedean property for any complete ordered field. We have a nice corollary. Of this. Corollary. In any complete ordered field, F, we have number 1, the subset N is not bounded above, given any epsilon greater than 0, we can find n naught in n such that 1 by n is less than epsilon whenever n is greater than n naught. Proof. For the first part, take x equal to 1 in the previous result. If you take x equal to 1 in the previous result, what you will get is the set n such that n is in n, which is same as the natural numbers. That set cannot be bounded above, because the entire proof of the previous result was that if the set is bounded above, you get a contradiction. So just taking x equal to 1 in the previous result immediately gives that the natural numbers are not bounded above in any ordered field. For part 2, take y equals 1 by epsilon and x equal to 1 in the previous result. Okay. So what you get out of the previous result is that there is an n naught, there exists n naught in n such that n naught x is greater than y, or in other words, n naught, where x is 1 now, so n naught is greater than 1 by epsilon. Okay. Or in other words, 1 by n naught is less than epsilon. Okay. But from the fact that n naught plus 1 is greater than n, we get, n plus 1. From the fact that n plus 1 is greater than n, we immediately get 1 by n plus 1 is less than n. So if n is greater than n naught, then 1 by n is also less than epsilon. Okay. So from the Archimedean property, we have concluded that the natural numbers are not bounded above, and the fact that 1 by n can be made as small as we desire. This epsilon plays the role of smallness, and we can make 1 by n as small as we desire. Note one more thing, that only the Archimedean property was used in this corollary. Another corollary is we can improve the nested intervals theorem. This I call the nested shrinking intervals. The nested shrinking intervals. What this says is the following. Let II, which is AI BI, be nested closed intervals as before. Let them be nested closed intervals in a complete ordered field F. Assume further that for each n in n, we can find I in n such that modulus of bi minus ai, in other words, the length of the interval ii is less than 1 by n. Then intersection of ii is a single element. Okay. Note that in the nested intervals theorem, we just have that the intersection of the ii is some non-empty set. Now we are saying that it's going to be a single element. Let a comma b be there in the intersection. Note that the fact that there is at least one element in the intersection is guaranteed by the nested intervals theorem. We have to show that there isn't more than one. And recall that in such scenarios, we assume that there are two elements and show that both are same. So let a comma b belong to the intersection of ii. Okay. Set mod a minus b to be equal to epsilon. Okay. This is a positive quantity. Okay. So set epsilon to be mod a minus b. This is a positive quantity. By the previous corollary, we can find n naught such that 1 by n naught is less than epsilon. Okay. But by hypothesis, we can find I in n such that mod bi minus ai is less than 1 by n naught is less than epsilon is equal to mod a minus b. Okay. So the length of the interval ai bi is less than mod a minus b, which means it is impossible that a comma b is present in ii. Okay. So this shows that intersection of ii has only at the max, at most one element. Okay. So this shows that when you have nested shrinking intervals, the intersection is precisely one element. Let me end this module by summarizing what is it that we have achieved. Our original objective was to find a an appropriate ordered field that contains the rational numbers yet has no holes. We wanted to get a one-to-one correspondence between this ordered field and a straight line, points on a straight line. The nested intervals property, together with the Archimedean property, neatly captures the fact that there are no holes. We will discuss this more in the next module. At a first glance, it might seem like just the nested intervals property is enough. Look back at the picture that I drew when I proved the nested intervals property. If there is a hole, you can just surround it by nested intervals and get rid of the hole. Say that this hole is not really there. But actually, you need the Archimedean property to trap this hole inside closed intervals. We will see that in the next module when I prove that nested interval property plus Archimedean property actually implies completeness. Now, since you need both, the question arises, are there ordered fields that satisfy the Archimedean property but not the nested intervals property, and vice versa? Now, we will not supply examples here. In the notes, I have referred to a paper in which this is discussed at great length. This is a course on real analysis, and you have just watched the module on the nested intervals property and the Archimedean property.